Hi there, ladies and gentlemen. This is Mr. Workman, and I'm going to take you through some very basics in terms of atomic structure and matter, and how we can draw some Bohr models that relate to atomic structure. And we're going to talk a little bit about isotopes. So let's get started right away here. As you see over here on this side of the screen, this is a really very general looking diagram that many of us attribute to science. Really what it is it's a rudimentary and general diagram of the structure of an atom. And you should be able to make sense out of that after viewing the screencast today. Questions you should be able to answer after viewing the screencast. You should know what matter is. You should know what chemistry is, and you should know what atoms are. You should know what atoms are made up of, and you should be able to tell a particular type of atom, the type of atom that you're looking at, if you can see the protons and neutrons in a diagram. You should know what a Bohr model is, and you should know what isotopes are. So let's get right to it here. Again, we're going to go through matter, atoms, elements, and isotopes. So those are some key words to be on the lookout for here as we go through the screencast. First of all, I want to let you know that all things, everything, is made up of this stuff we call matter. Matter is anything that has mass, matter is anything that takes up space. And chemistry, because it's the study of matter and the interactions of different types of matter, can really be described as the study of anything that is. So if it is, it's chemistry. Now, you need to know that matter is made up of basic building blocks we talk about that are called atoms. And atoms are made up of these subatomic particles that we're going to get into later. And what you're looking at right here is just a very, again, rudimentary general diagram of the structure of an atom. We know that protons and neutrons are subatomic particles. These are particles that are less than an atom. They're found in the nucleus. And electrons are found to orbit the nucleus of atoms. Elements are substances that are made up of just one kind of atom, and what makes one kind of atom different from a different kind of atom is going to be explained later. There are about 100 elements that we know of that exist, that we know of today. Elements that have atomic numbers that are higher than 92 are elements that are actually made by humans. The heaviest naturally existing element is atomic number 92, which is uranium. And the rest of them are called transuranic elements that have been produced in big, huge super colliders where we smash protons together, and they happen to stay together for a little while so that we can figure out what that means. These particular elements are really important for biology. So if you've taken a biology class, you'd know that carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur are the elements that are the really important elements for living matter. In fact, they make up about 97% of the mass of the compounds that are found in living things. Something that's interesting to note is that matter and atoms that we can see, well, not really see, but determine that are part of matter, these types of atoms are the same not only just from our planet, but from other planets and other substances that seem to come from not of this planet. So when we study things like meteorites or moon rocks or things like that that are, of course, not directly from Earth, what we've been able to determine is that it doesn't really matter, no pun intended, where something came from. It seems that matter is the same everywhere. So an iron atom from Mars or an iron atom from a meteorite is going to be the same thing as an iron atom that's found in rocks of the Earth. And that's just an interesting thing to talk about. This diagram is a diagram of something called the periodic table of elements. And elements are the different kinds of atoms that exist in this universe. Again, some of them are man-made. This one down here, this uranium atom, is the heaviest type of atom known to exist that's a natural atom. So there's a reason why these different types of atoms, or these elements as they are called, are arrayed or arranged on this table in the way that they are arranged, and we'll be talking about that later as we progress through our chemistry class. Now, using the periodic table is going to be important, and what I want you to be able to do is interpret the information that's in each of those boxes on the periodic table. And if you can figure out how to do that right, you can really glean a lot of information about the structure and what's in an element in the atom of a particular element that you're looking at if you can figure out what the information in the periodic tells you. So I'm going to go back to the periodic table for just a second and just show you, and we can zoom in here on this particular hydrogen, or perhaps I can zoom in on this particular iron here. And what you'll notice is that in these little boxes are numbers in these boxes, and then of course letters as well. So let's go back to the next slide and just make sure that you realize what this is. Generally in periodic tables, the numbers above these letters is something called the atomic number. And the letters here, which is going to be either one capital letter or one capital letter combined with a lowercase letter, or in some instances one capital letter with two lowercase letters after that. That's called the atomic symbol. Now you might think of it as an abbreviation, and for some of the elements that works, but for some of the elements, some of the other elements, the letter that's the symbol is not going to have anything to do with the English name that we use to describe an element. So we refer to this as a symbol and not an abbreviation. The number on the bottom is called the average atomic mass, and it's actually a weighted average, which is why some of the numbers are not whole numbers. In fact, almost none of the numbers are whole numbers on the periodic table. So if you can interpret what this information means, you can learn a lot about the structure or the arrangement of particles inside each type of atom. So let's start to figure out how we do that. So when you interpret the information in each box in the periodic table, you look at these numbers, and what that should be able to let you know is, including these things, the number of electrons, the number of protons, and you should also be able to figure out the number of neutrons. So how do we do that? Well, this is a really, really simple Bohr model, which basically you just draw the number of protons and neutrons that there would be in the nucleus, and you draw the number of electrons that would orbit that nucleus. This is a simple Bohr model of hydrogen, and the way that we arrive at this is by looking at the information in the periodic table. So I'm going to go back to this. This number right here tells me the number of electrons, and it tells me the number of protons. As long as I'm dealing with an atom here, the protons will be the same number as the number of electrons, and this number is a 1. Now this number down here is going to tell me how many protons plus how many neutrons there are in the nucleus of an atom on average. Well, this number is really close to 1. So what that means is, it probably means there's just 1 proton and 0 neutrons, because 1 plus 0 is 1. And that's what this is. This is 1 proton. There's no neutrons in a typical hydrogen atom, and there's generally 1 electron that's orbiting that 1 proton nucleus in hydrogen atoms. So let's talk about some of these particles and make sure that we know the different types of particles. Let's make sure we know what kind of charge they have. Let's make sure we know what kind of location, where they're found in the atom, what their mass would be, and what their function is. So this is, again, here's our 3 types of subatomic particles that I'm going to want you to know about. And as it turns out, with greater and more interesting research that's been going on more recently, there are particles that make up these subatomic particles, things like up quarks and down quarks, and now the infamous Higgs-boson particle. I don't know if you've heard anything about the Higgs-boson particle, but it was discovered just this summer, although it was hypothesized to have existed much longer before that. But these are not things that are going to be, we're not going to worry about that in the context of a high school chemistry class. So what I want you to know about are protons, neutrons, and electrons. Protons, of course, are particles that have a positive charge. They are found in the nucleus of an atom. They have a mass of what's called 1 atomic mass unit. And protons really determine the identity of the element that we're dealing with. So it's the number of protons that's really important to figure out what kind of atom you're talking about. Neutrons are subatomic particles that have no charge. They are also found, like the protons, they are found in the nucleus. They also have a mass of 1 atomic mass unit, and their function seems to be to lend stability to the nucleus and holds the nucleus together. In some instances, if you don't have the right number of protons and neutrons combined, the nucleus seems to be unstable, and when you have atoms that have unstable nucleus, that results in something called radioactivity, which is something we will study later on this year. Electrons are particles that orbit the electron, the atomic nucleus in what's called the electron cloud, or sometimes it's referred to as electron orbital or level, energy level. And I don't really care what you call it. I just want you to know that electrons are not found in the nucleus of atoms. They have a negative charge, their mass is pretty tiny compared to the protons and neutrons. They are about 1/2000th, more precisely 1/1840th the mass of protons and neutrons. So if you have 1,840 electrons, that would add up to the same mass as one proton or one neutron. And it is the amount of electrons and where those electrons are in an atom that's going to determine how one type of atom might interact with another type of atom, or whether or not it would interact or react at all. Now again, let's talk a little bit more about how these numbers on the periodic table can tell us something about the structure of atoms. The atomic number, of course, is always going to be equal to the number of protons that are found in an atom. So, for example, if we're talking about carbon here, it's got an atomic number of 6, which means that in the nucleus of every carbon atom, that's what defines carbon as carbon, is if there are 6 protons. The mass number is going to tell you the total number of protons plus the number of neutrons. So I'm seeing down here this number is 12, which would let me know, because there are 6 protons and there's a total number of 12 nuclear particles, so the mass number tells you how many nuclear particles there are. 12 minus 6 would tell me that there are neutrons. So again, what you can do to figure out the number of neutrons is take the mass number, which is this number down here, the 12, and then subtract the atomic number, which is this number up here on the periodic table boxes. And then the difference between those two numbers is going to be your number of neutrons. And generally what you do is you round to the nearest whole number to figure out the number of neutrons, because what I'm not going to do is say that there are 6.01 neutrons in a carbon atom. That just doesn't make any sense. When you have something that is referred to as a neutral atom, that means that your number of electrons is going to equal your number of protons. So in a neutral atom of carbon, I would have a total of 6 electrons. And as it happens, 2 would be in our first little level of electrons, and there would be 4 in the second level. 2 plus 4 is 6 when we're talking about a carbon atom. An ion is a situation where your number of electrons do not equal your number of protons. And this is something that happens to some elements that are on the outer edges of the periodic table, although sometimes you can get ions from elements that are in the middle of the periodic table as well. And there's a pretty general pattern that we can use to predict how elements will turn into different charged ions. This is a good example of one of those elements and how it can turn from an atom into an ion. As you look at the configuration of this particular atom down here, what we have is chlorine. And the reason it's chlorine is because there are 17 protons. Most chlorine atoms exist with 18 neutrons in their nucleus, so the average atomic mass for chlorine is somewhere really close to 35. If you look at 17 and 18, add those together, well, that's 35. A chlorine atom is going to have a total of 17 electrons. There's 2 in this first level, there's 8 in this second level, and then there's 7 in this third level, or this third orbital, as it might be called. And these numbers 2, 8, and 7 refer to the number of electrons in those levels respectively. And if you add 2 to 8 to 7, what you get is 17. So the reason I have a chlorine atom here is that my total number of electrons is equal to my total number of protons. Well, as we'll start to discover here, when atoms don't have full outer levels, and the outer level is referred to as the valence level of electrons, it seems like they're unstable. And so what atoms will do in many instances is either empty their valence levels, or as the case here, they will fill their valence levels by gaining electrons. And what chlorine can do is gain 1 more electron, and the result is that there's, again, 2 electrons in the first level, 8 electrons in the second level, and then now there would be 8 electrons in the third level, which means 2 plus 8 plus 8. That means there's a total of 18 electrons here and 17 protons, and because there's an inequality in the number of electrons and protons, we have a charged ion. This is the configuration of a negative chloride ion. And I know this is not the same thing, the chlorine and chloride. What happens is many times what the chemistry language changes when an atom turns into an ion, especially negative ions. Very often the element names that end in INE, when they ionize, they turn into negative ions. They'll turn the ending of the word, or the suffix of the name for the word, will change from INE to IDE, from ein or een to ide. So again, let's review this. The atomic number is going to tell you the number of electrons and tell you the number of protons, but that electron statement is only true if we're discussing an atom and not an ion. The letters in the middle here are the symbol name and not an abbreviation, and this number down here is the average atomic mass in atomic mass units for these elements. So what I would hope that you would maybe try to do here is maybe try to draw some diagrams of hydrogen and oxygen and nitrogen atoms, see if you can figure that out. What you should do is, again, draw one proton with one electron for a hydrogen atom. For an oxygen, you'd have 8 protons, and this number is really close to 16, so most oxygen atoms exist with 8 neutrons. 8 plus 8 is 16. And you draw 2 electrons in the first level, and you draw 6 electrons in the second level for an oxygen atom. In a nitrogen atom, you'd have 7 protons in the nucleus, you'd have another 7 neutrons in the nucleus, you'd have 2 electrons in the first level, and then you'd have 5 electrons in the second level to make a nitrogen Bohr model. Isotopes are sort of weird situations. It's just when you have the same type of element, so that would mean the same number of protons, but the number of neutrons is different than what the average number of neutrons would be. So for example, carbon-14, it's still carbon because it's got 6 protons, but it's got 8 neutrons. So that's why it's called carbon-14, because 6 plus 8 is 14. Carbon-14 is something that can be useful to determine the age of fossils, and it can be useful in biological research. And even other radioactive isotopes, we call those radioisotopes, can be used to figure out or diagnose patients in particular situations during medical procedures. So that's it for this particular screencast. We're going to work on drawing Bohr models in class so that we know how to interpret information from the periodic table. But this is just a really general introduction to that stuff. So you should have some answers to these questions. What are matter? What is matter? What are atoms? What are ions? What are the different types of atoms called? Elements, and what are isotopes? So hopefully you learned something, ladies and gentlemen. Thank you so much. Bye-bye.